Welcome into our final video on Chapter 10, Nuclear Chemistry. Here we're going to be looking at some applications of nuclear chemistry, mainly involving kinetics and radiometric dating. As it turns out, radioactive decay processes happen with first-order kinetics. This is great. It simplifies our thought process greatly. We can already assume the order of our reactions when we have radioactive decay. Recall from our previous unit, the rate law describes our reaction rate in terms of our concentrations for our reactants. First order reactions have an exponent of 1 for our concentration. And if we know everything is first order, there we go. We can say the rate is exactly proportional to our concentration. In the past, we used our integrated rate law to derive a nice equation for first order reactions. And that looked something like this. The natural log of our concentration is linear when plotted against time with a slope of negative k at rate constant. The y-intercept was the natural log of our initial concentration. We can rearrange this equation a little bit by subtracting this natural log of our initial concentration and then using some log rules to combine these two logs together. When we subtract two logs, we can change that to this form where we have the division inside of our natural log and just a single natural log. The natural log of this ratio of concentration right now divided by concentration initially is equal to negative kT. This form of our integrated rate law is actually going to be a little bit more convenient for our radioactive decay processes. Sometimes we only care about that ratio of how much we have now versus how much we started with instead of the actual amount. And we can also look at, maybe 3 different forms of this. We can have what we just derived from our integrated rate law, this ratio of concentrations. We can also change our concentrations into actual rates. The concentration is exactly proportional to the rate. If we have a ratio of concentrations, we'll have that same ratio for our reaction rates. So for first order kinetics, we actually don't need to know the concentrations. We can just measure the reaction rate at one time, the reaction rate that we started with. And this will also follow that same equation. Likewise, the number of our atoms of our reactants is also going to be proportional to our reaction rate. We can use the same expression with the number of atoms, with our reaction rates, or with our concentrations like we've seen before. The fact that our rate is proportional to our concentration allows us to do this swapping in for our integrated rate law. This is not going to hold true for 0 or second order reactions, but that's good news. Radioactive decay is always first order. We can always do this little trick. Lastly, we can say our half-life for first order kinetics is going to follow this equation. Half-life is the natural log of 2 divided by our rate constant k, 0.693 divided by k. We know that our radioactive decay will always follow this first order kinetics, but different processes will have different half-lives. They'll go at different rates. Here's one example. Cobalt-60 is a radioactive nuclide with a half-life of 5.27 years. We can see this plotted over on the right. Maybe we have 100% of our cobalt-60 that we start with. In 5.27 years, we're going to drop down to 50% of what we started with. 5.27 years after that, we'll drop down to 50% of 50%. 25% of what we started with. After a third 5.27 years, we'll drop down to 12.5%, and so on and so forth. If we know the half-life for this process, we can describe the kinetics at every point along this kind of graph. Another example, thorium-232 also undergoes radioactive decay, but its half-life is 14 billion years. Well, same first order kinetics, but now our half-life is, well, longer than the universe has been around, but still we can describe how often we expect this to happen. All right, here's a third example. Radon-220 has a half-life of about 1 minute. Every minute, our amount of radon-220 will drop by 50%. Here's a practice problem. Cobalt-60 decays with a half-life of 5.27 years to produce nickel-60. By the way, this looks like beta decay. What is our decay constant for this process? We can use our equation for half-life to figure out our decay constant. We get a value here, 0.1315 per year. Question 2, we can try to find after 15 years how much will be left. We can use our first order kinetics equation. And what we're trying to solve for is this ratio of n divided by n0. How much do we have now compared to our initial amount? This is that fraction remaining at a certain time. What we end up with is 0.139, which is what we'd expect. 15 years is about 3 half-lives. The first half-life will cut us down to 50%, the second half-life to 25%, that third half-life to 12.5%. Well, here we're at, 0.139 is the same as 13.9%. We have 13.9% of our sample remaining, or as a fraction, 0.139. For question 3, we want to know the time it takes to get down to 2% of our original amount. Well, in this question, we have 2 compared to the 100 that we started with, right? 2% is the same as 2 out of our initial 100. We know this k value, again, from above, and so we just need to solve for t. We can solve this and figure out our value, 29.7 years. Again, we can do the common sense check. We want to have 2%. 29.7 years, does that make sense? That's about 6 half-lives. The first will get us to 50, then to 25, then to 12.5, then to 6.25, then to about 3% after 5 half-lives. The sixth half-life will get us down to about 1.5%. So yeah, that makes sense. Between 5 and 6 half-lives will get us to 2% of our original amount. We can take advantage of these kinetics and our calculations here in order to do what's known as radiometric dating. Since all radioactive processes follow that first order kinetics, have a constant half-life, we can calculate how long something has been hanging around and undergoing this radioactive decay if we know the amount that it's decaying at right now, and we know the amount we expected it to be decaying at years and years ago. Carbon-14 is particularly useful for this radiometric dating process for a few reasons. When plants are alive, they use the carbon in the atmosphere to do photosynthesis. Some of that carbon is carbon-14, which is radioactive. As our plant is alive, it is putting carbon-14 into itself so that it has the same ratio as the amount of carbon-14 in the atmosphere. However, once our plant dies, that photosynthesis process no longer occurs, and no more carbon-14 is able to be put into our organism. What that means is, as soon as our plant dies, there's no more carbon-14 being added. It's going to slowly decay based on first order kinetics, based on this radioactive decay process here of carbon-14 turning into nitrogen-14. What that means is now we can measure how much carbon-14 is in our organism, and we can work our way backwards based on the known amount of carbon-14 that was in the atmosphere throughout the course of history. This allows us to date things out to about 30,000 years old because the half-life for carbon-14 is about 5,700 years old. Beyond this point of about 30,000 years, our method is much less accurate. We need to be within maybe about 5 or 6 half-lives, then our precision becomes much, much lower. Here's a practice problem we can work through. We have some seeds and plants from King Tut's tomb, and they have a C14 decay rate of 9.07 disintegrations per minute per gram. We know that decay rates for C14 are 13.6 disintegrations per minute per gram for most plant life. Based on these decay rates, can we figure out how long it's been since our plant was able to regenerate the amount of C14 in itself, how long it's been undergoing this radioactive decay? We can start by finding our rate constant, K, 1.209 times 10 to the negative 4 per year, based on our half-life. Next, we can use our first order kinetics using our decay rates. Remember, we said we can use concentration, we can use number of molecules, or we can use these actual rates as long as our reaction is first order. We can find here that our plants have been dead for 3,350 years. We mentioned that carbon-14 is good to about 30,000 years for radiometric dating. What if we want to measure things that have been around for longer than that? Well, you just need to find a different radioactive isotope that's been around. Some good choices, we can look at the uranium in our rock samples, for example. This has a half-life of 4.5 billion years, so we can measure how old things are on the scale of billions of years. Likewise, argon-40 has a half-life of 1.25 billion years, also good on that timescale. Even longer than that, Rb-87, great. 50 billion year half-life, we can measure things that are very, very, very old. Using these processes, some rocks in Australia have been radiometric dated out to about 4.4 billion years old. Since we have rocks on the planet that are that old, we can assume that the Earth is at least that old, 4.4 billion years old. And with that, let's call it a day here. We said we can consider how that we know our ancestors are 3.2 million years old. Our planet is around 4.5 billion years old. Artwork has been around for 40,000 years. Well, using these known first order kinetics from our radioactive decay processes. The thought we had to consider, why is this process going to be in danger within the next few decades? Well, the answer is that we've been burning lots and lots of fossil fuel. Burning fossil fuels at this tremendous rate has increased the amount of carbon in the atmosphere. In order to do our radioactive decay carbon dating process, we need to know how much carbon there was when this thing was around, and we need to know how much carbon was in the atmosphere when that thing was around. If the amount of radioactive carbon in the atmosphere is changing, well, our process is going to be less reliable. Since we're releasing all this carbon into the atmosphere from really old, fossil fuels, really old sources of carbon, where the carbon-14 has already disappeared, that baseline amount of C14 in the atmosphere is getting lower and lower. And so this is something you need to account for when you're thinking about how old things might be. Instead of just doing this carbon dating process, maybe you also need some extra evidence to prove that something is as old as we think it. All right, thank you for hanging in there. This will complete our lesson here on Chapter 10 and for our series. As always, please do not hesitate to reach out with any questions you might have. I am happy to be in touch. Thank you for being here, and I hope you have a great day.